How are you doing?
Great.
Fine.
Travel arrangements okay, Pratyush? You're leaving tomorrow.
Yes, yes, yes. It's more or less okay. All documents have been sorted out. And yeah, I think we both are good to go. Yeah.
Good. So, do you think Nitya will join us today?
Yeah, she will. I think she will be 5 minutes late,
Okay, good,
something like
good
that.
then.
Yeah.
Okay, then I think we should wait for her a little bit. I'll give her a few minutes to join us. Okay. Hola, Felipe.
Okay. Okay.
Let's give her a couple of more minutes before we start. I want to discuss the exam I just sent and summarize a little bit what we've seen so far. So we'll give her a few minutes. We'll just continue. Where was I? Okay. So yes, we wanted to look quickly at the textbook. No. Okay. Okay. So last time we looked at the textbook. I think what's left of chapter B, chapter 2 was where did we leave it? I think we left it there here at section 2.2, and
I think we covered the basics of radiation spectrum.
so oh yeah, we already went through that as well. Did we look at this? No, I don't think we did. I think we are, yeah. So that's right. So we need to go through section 2.3. But today I want to make sure that we make some more efficient progress. And I'd like to start directly with my summary and then ask for one of you to describe very briefly what's in section 2.3, if we have time. Okay, so I want to start with polarization. So last time we looked at the continuity equation. Oh. Yeah. Hello, Nitya. Are you okay?
Hello, Professor. Yes, I was stuck in traffic. I'm sorry.
That's okay. That's okay. Are you okay for leaving tomorrow?
Yes, Professor. I'm fine now. Yeah.
Good. Great.
Use
Great.
it with me now. I'm confident.
So I hope you have a nice trip tomorrow and that everything goes smoothly and that you'll soon be in quarantine in Chile. So with nothing to
Yes.
do but solve an exam. Maybe you have a few more things to do actually. Sorry, but
No problem.
so I shared the exam yesterday evening. Normally, the exam is meant to be carried out in 3 hours with access to internet and textbooks and everything. But of course, it's personal work. Now, given the pandemic situation and Pratyush's and Nitya's travel tomorrow, I've decided to extend the time you have to solve the exam to 1 month. Okay, so it's, I mean, as I say, I mean, you should be able to do this in 3 hours. Of course, like the intense 3 hours is not like, I mean, I don't mean like 3 hours like easily. No, it's going to be intense in 3 hours. Just so you bear in mind that this is not a month worth of work. I'm just giving you a month just so that it doesn't represent an extra source of pressure. I do not want to press you. Okay. So this is that's the idea. It's not an exam that will last 1 month. It's just that you have a month because I don't want to press you. Okay. Please do not discuss the exam with between yourselves or with anyone else. We can discuss it after you've handed it in. Okay. So I don't know if you have any questions about it or. It's okay. You remember that the exam is using references. So if I point at references, it's for something you have to look at the references. It's the same as in a paper, you know, like when you read a paper and you see a reference, it means that the reference is supporting a statement. And if you want to know more about it, then look at the statement, look at the reference to understand the statement, you know. I assume that you all know where to find the papers. So are you all familiar with NASA ADS? Is someone not familiar with NASA ADS? Okay, so we all know what I mean. Good. So let's continue with the topic at hand. So I was saying.
I have a question. Sorry,
yeah.
no, short question.
Yep.
So what does half the mark for substitution means? It's on some of the questions that you wrote, half the mark for substitution.
Yes, because one thing is to because you can reach at the you can reach the radiation transfer equation. You know, like you can derive it, or you can confirm that it works. I mean, you can confirm that the solution to the radiative transfer equation works by substituting the solution into the equation, or else you can derive, or else you can reach the conclusion without knowing it. So suppose that it's the first time that anybody solves the radiation transfer equation, and I'd like you to describe the reasoning to reach that solution. So of course, if you have the solution, you can always check it works by substitution, is what I mean. Okay.
Okay, thank you.
Okay. So last time we were looking at the continuity equations for the radiation energy. So that was the Poynting theorem. The most important part is this one, equation 23. So this is the continuity equation for the radiation energy, which is given by equation 21. And the radiation flux then is a Poynting vector. Okay. And this would be the power lost in accelerating charges. So this is like a sink. So you can lose radiation energy by transporting it with a Poynting vector, in the form of waves, as we're seeing at the moment. Or you can also lose radiation energy by accelerating charges. Okay. So then last time we looked at the spectral decomposition. This is the Fourier transform. And when you plug in the spectral decomposition into the wave equations, you get the Helmholtz equations, Helmholtz, whose solution are also oscillating exponentials. So that in general, each component of the electric and the magnetic field can be described by a superposition of plain electromagnetic waves or monochromatic waves with an amplitude, a complex amplitude, which we usually call the spectrum. This is quite simple. You can rewrite same equation by factorizing k, the wave number, in the exponent. And this form is similar to D'Alembert solutions for the wave equation, which makes it clear that these are traveling waves. When we have the minus sign, it's traveling towards plus v, and with the plus sign, it's traveling in the opposite direction. Okay, and we can also show that these waves are transverse, meaning that the electric and magnetic fields are perpendicular to the direction of propagation, and that they form a direct triad, so that E cross B equals N is proportional to the direction of propagation. So also we looked at the complex notation, and so the complex notation, of course, is very customary to use in electrodynamics, but you have to bear in mind that the fields themselves are real, and that's particularly tricky when you take products like these. So it is a mistake to calculate the Poynting vector using E and H as in complex form, and then take the real part. You have first take the real part and then take the cross product. Okay. So it's because of the way we measure radiation flux, we need to take time averages, and this is well, we need to take time averages of this radiation flux of the Poynting vector, and this involves taking time averages of this type of quantities, also the real part of complex numbers, of the product of complex numbers. And it turns out that we have equation 35, which is quite handy to calculate time averages. For the time average Poynting vector, we see that time average is proportional to the squared amplitude of the electric field, and similarly for the radiation energy density. And we have this very interesting relationship with so valid for a plane wave, where we have the radiation flux, the Poynting vector, is the energy density multiplied by the phase velocity, the traveling, the speed of light, basically. And so then we looked at the connection with radiation transfer, where the idea here is to relate, because we defined the radiation flux in terms of this first moment of the specific intensity field. So the radiation flux at point X is the first moment of the specific intensity at this same point X. We are averaging over directions K, okay? And so in order to connect with the Poynting vector, so we said that the Poynting vector then is the flux of energy in the direction K, okay? How do I know this? Because, well, I'm applying the continuity equation for radiation energy in the case of a plane wave. So we know that Maxwell solutions lead to the wave equations. So these plane waves are solutions of the Maxwell equations, and they describe signals that propagate in some direction K in this case. And we see that for this plane wave, the Poynting vector has a time average, which is the energy density times the speed of the pattern, which is the phase velocity here, okay? And so this has the dimensions of radiation of flux of energy in direction K, okay? We want to connect this S with the specific intensity. And the first thing to realize is that the flux is given by the first moment is just the same as the Poynting vector, as the time average Poynting vector, as the norm of it actually. Let me write this down. So we have this plane wave traveling in this direction k. Okay, so that's the wave. So here I'm drawing, for instance, the electric field. Okay, and so we can calculate S, which is E cross H. Okay, and we know that that this is the the flux of radiation, because in time average, the time average of S is then going to be the speed of light times the energy density in the direction k. Okay, so you know, I think it should be clear to all that this is the form of a radiation flux. Like if I take like little balls, you know, and I tell like balls, you know, flying in the direction k, you know, and you have this detector with a cross section A. Then we've looked at this several times, you know, but I just want to connect that the flux, let's call it Q, just well, no, maybe F is the same. The flux of a number of balls that are going to cross this section in per unit time is given by the density of such balls times their velocity. Okay, so they're all, so V is all pointing that way. Okay, so and this is the standard way of expressing the flux. You simply the argument you've seen many times, I'm sure, is just to, you know, compute the number of balls that would reach A in some amount of time delta t. And so this would be all the balls that are enclosed in this volume whose height is given by delta t times v, you know. And so you say, well, the number of balls that are going to cross this such cross section is going to be the volume times A multiplied. So this is the number of balls multiplied by the density. Okay, and so F is none other than this number delta n divided by delta t A. Okay, so this is just a brief reminder that when we mean a flux, when we mean the density of whatever is being fluxed or being transport times its velocity. Okay, so when I write here, that would be the energy density, and that would be the speed. Okay, so it's the same as here. We have the density and the speed. Okay, so this form makes it also clear that the Poynting vector is a radiation flux, exactly as the flux we mean when we look at the first moment of radiation energy. Okay, so we looked at this in detail in chapter 1. This is just a reminder of what we saw in the last lecture. Okay, and so we said that F nu F nu is just the same as S nu, as the norm of the Poynting vector. Now, how does this connect with the specific intensity field? Well, you know, we need to have this relationship. So we need to have something, the specific intensity field for a plane wave then is going to be this at some point x, k z k naught, okay? And we need this to be equal to the norm of S. And for this to work, you know, we need y nu to be the delta function. So this is how we connect this specific intensity field with this specific intensity field with the Poynting vector. Okay. Good. So we saw this last time, and now we are getting on with polarization. And so, well, first of all, let me show you the sketch, which is in the next slide, actually. So this is what a generic electromagnetic wave looks like. So we have a plane transverse wave, you know, and we define a set of Cartesian as a Cartesian basis. Okay, so we have E1 and E2. So that would be the plane of E and B of the electromagnetic field. Okay, and so going back now, in general, any plane monochromatic wave, so any monochromatic component actually can be decomposed as equation 40. So this comes from the spectral decomposition. And so we have these amplitudes E1 and E2. And these are understood as complex amplitudes. So we are embracing the complex notation here with a complex notation for each monochromatic term, okay? So this, in general, describes an elliptically polarized wave. So I'm sure you've heard of this before, but given the importance of polarization in astrophysics, it's worth having a look at it again. Well, I try to do this as quickly and efficiently as I can. So, for instance, if E2, so if E2 is 0, then we have that the electric field is just E1 times the exponential the oscillating exponential in the direction E1, and you can imagine that this electric field is going to be oscillating only in direction E1. Okay, that's what we call linearly polarized. Okay, in general, this is going to work as long as there is no phase difference between E1 and E2. So to make this obvious, you know, as long as we can make, yeah, so the idea is to factorize, yeah, so there's no complex phase difference between the two components. So if, how do I write this? Yeah, well, I should write this down like this. Epsilon 1 E I delta 1 and E2 like that, okay? So if we have that delta 2 equals delta 1, then we can write E as exponential I delta 1 times epsilon 1 times, sorry, I'm going to factorize here the oscillating exponential times E1, yeah, so epsilon 1 along E1 plus epsilon 2 along E2. Okay, and this is just a real number. This is all in R, you know. And so this again describes just a linearly polarized wave. Okay. Now, what happens when there is when delta 2 is not equals to delta 1, when there is a phase difference between each component, you know? So in this case, we have an time dependence difference between the two components. And one way to see this quite clearly is using this trick. Like, just want to emphasize, like, you know, like, if I take the dot product of E1 dot E1, that would be the linearly polarized components along E1. You know, and if I take E dot E2, then I also get the same thing, but along the other Cartesian component. You know? Now, there is an interesting trick to be done, which is a change of basis to these two sets of vectors. So we have E plus now, which is 1 over square root 2 times E1 plus I E2. And then we have this E minus, which is E1 minus E2, I E2. Okay, so let's define these two new unit vectors, and they're complex. Now this time they're complex, okay? So we can turn this system around and write E1 as a function of E plus and E2 and E minus. So in order to do so, you first subtract both of them. And so we have E1 equals square root 2. Let me see if I subtract the 2. Yeah, times E plus minus E minus. No, it's plus. Let me see. If I sum both of them, then the E2 gets away, and I have E plus. Yeah, that's that. Please correct me if I overlook something. And then E2 is gonna be very similar. So it's square root 2. It's E plus minus E minus. Almost there, because when we put a minus sign here, it's going to be, yeah, so this one goes away, and I get...
that E2 has an I
yes.
also.
In its, I think in the denominator, so... okay, so thanks, Felipe. Is this correct now?
Not with the minus sign. It's in the numerator because you're only subtracting, not dividing. You get 2 times I E2 divided by the square root of 2.
Oh,
yeah.
Hold on. So, so that would be, this is wrong too.
No, it is that is good.
No, I think that should be 1 by root 2.
Square root of 2. The minus on the minus sign on the
Yeah.
second is not there. Shouldn't be
This
there.
one.
Yes.
Let me think. Let me think a little bit. It's just
No, on the square root of 2. That should be there on both.
yeah. Wait. I just want to.
I think it should be 1 by root 2. Because if you add the two equations, so it will become 2 by root 2, which is just root 2 times E1 no, what to say, E1. So if you so if you divide, then it will be 1 by root 2.
Is the square is root 2 okay now, Pratyush?
Yeah, I think it should be in denominator. I think this iota.
Yeah, I think it's okay, but I think there is a minus sign here.
No.
Do we agree that there is a minus sign, or Felipe, or you still think that there isn't?
I'm doing it here.
Yeah, no, it's okay. Let's just check. Take the time, please.
2 seconds.
I tend to go too fast and I always make mistakes by going.
In my case, it is not minus sign in front of that. Like
Okay.
I under root 2 E2 is
Yeah.
equals to E plus minus E minus in my case.
No, sir, it's fine. It's fine, I think. Because if iota is in denominator, then I'm multiplying in both numerator iota by iota, so it will be minus. I think that's fine. At least for me, it's fine.
I'm just waiting for Nitya and Felipe to cross-check, so we all agree.
Yeah, like it should be minus in front of that. Like if you will solve iota, then it would be minus.
Okay.
Yes, I also say
Okay, then-
there's a minus.
Okay, it's not so important anyways, but this is a bit of a mental exercise for the morning. So let's plug this in. So we have that the electric field given by equation 40 then is going to read out 1 over square root 2 E plus E minus times E1 times this oscillating exponential plus E2, which is a minus actually, minus 1 over square root 2I times E plus minus E minus E2 times the oscillating exponential. So what I did is just plug in E1 and E2 into equation 40, okay? And in the end, we see that we can group each E plus and E minus together. And so we have E plus times 1 over square root 2 factor of E1 minus I E2. And the other component is E minus times 1 over square root 2 times E1. Sorry, yeah, it's okay. I think it's correct. Plus I times E2. And in both cases, we have this oscillating exponential. Okay, and so this is what we call these terms here are what we call E plus, and this is E minus. Okay, so that this was a bit weird. I'll rewrite it. Okay, and this I think this is the stroke recognition, which is playing some tricks on me. Let me write it again. So, and this, oh, sorry. E minus, okay. And so this is what I'm writing as equation 41. So I've rewritten this electric field in terms of this new basis, which is like a trick, if you want, where I've introduced this new basis of unit vectors. But no, they're not real, right? Because I'm multiplying one of the Cartesian components by imaginary I. But so I still can, then I can write both components in this way. Now, what's interesting to note is that E plus and E minus have a phase difference. If you So if you look at the case for E minus equals 0. So if E minus is 0, then the electric field is given by this E plus, which is going to be some complex number. Let's call it, no, I was using epsilon plus times E to the I delta plus. So I'm writing, this would be the Eulerian notation for complex E plus, okay, times the time dependence times E plus, okay. Okay, and so that's just a complex number. It's a number that's factorizing E plus with an exponential term here, okay? And so remember now that E plus is given by 1 over square root 2 times E1 plus I E2. And we see that the above equation then can be connected to a real field by taking the real component. The idea is to take a real component of E, and that's going to be, so E plus is going to be 1 square root 2 here. So 1 over square root 2 times epsilon plus times the cosine of the phase, which is going to be k times x minus omega t plus delta plus. Yes. And that would be along E1 plus yes, that's correct. And I need also that's the real component. The real component along E2 is going to be 1 over square root 2 epsilon plus times the cosine of kx minus omega t plus delta plus pi halves because of the I term, right? So this one here comes because of this factor. Do we agree on this real part?
Yes.
I think so. I think so. So now we must use a trigonometric identity here, which is the cosine of whatever angle plus pi halves is equals to the sine, right? I think this is the sine. Please correct me if I make a mistake here. This is the sine of kx minus omega t plus delta plus. Okay. So if we place ourselves Andrés, ¿estás pudiéndote conectar? Parece que tienes problema.
Ahora sí, no sé qué pasó con Zoom y Ubuntu.
Ah, sí, es inestable. Tengo problemas también a veces. Okay, so anyway, this should be standard. If we now, this makes it obvious that this is a circularly polarized wave because of the following reason. Like if we select just to make things really simple, suppose that we choose an x an x such that kx plus delta plus is 0. Just, well, it can be any value for this constant, really. But what I mean to say is that what we have now then is this. We have this electric field, okay, and it's these are the unit vectors, you know, and so we have that this component along E1 is epsilon plus over 1 square root 2 times the cosine of omega t, and the other one, well, it's minus omega t, strictly speaking, and the other one is 1 over square root 2 epsilon plus, so the same amplitude, times the sine of minus, let me write it again a bit further away, 1 square root 2 epsilon plus times the sine of minus omega t. Okay, so in other words, this angle here is minus omega t. Okay, so as time grows, this angle is going to become more negative, and so this is describing a which way will it rotate? It's going to rotate that way.
Professor,
Mhm.
I think cos theta plus pi by 2 is equal to minus sine theta, I think.
It's possible, because I mean I get the other direction of rotation. So so you're saying that Pratyush, you're saying the cos of theta plus pi house is minus the sine?
Minus sine theta. Please correct me if I'm wrong, anybody. Because
Let me see.
Yes, because when you plot the sine with the angle and you move the cosine
Oh yes,
up
yes,
to
yes,
the
absolutely.
left,
I
you
agree
get
with you.
minus sine.
Thanks very much. So so this is correct. I mean you're right. And it's good, because I was reaching the opposite conclusion. So this is going to be a minus here. I'm going to write it in red. So there's a minus here. And so this is very good, because now I've got that, I can, you know, this is an even function. So put the plus here and then the plus here, and that's good. The correct direction of rotation is counterclockwise. Okay, so this is the correct plus, E plus. So in other words, the E plus component selects a circular polarization in plus direction, so counterclockwise. So I think this should be standard to you guys. I'm sorry if I've bored you with this. What might not be so standard is this trick of selecting polarization by taking the dot product of E along E plus. So that's going to be a plus or circular polarization, and then E dot E minus is going to select the other one. Okay, so we saw how to select the linearly polarized polarization, linearly polarized waves, and this is another trick to select circular polarization. Good. We in general, you know, we saw the case for linear polarization when there was no phase difference between the complex amplitudes of the electric field. And the circular polarization is when the phase difference is exactly by half, okay, and we have the same amplitude, which is what we did by changing to this basis. If we take if we select E minus or E plus equals 0, we are restricting ourselves to this case. But the general case is elliptical with well, this is a sketch of it, so I won't bore you with how we calculate this the plane of polarization. I mean, you must have seen this before, but this angle chi then is given by this value here. Basically, it depends on each component. In general, any monochromatic component is always polarized, and in general elliptical. Now, this ellipse can sometimes collapse into linear polarization, and sometimes it just happens to be circular, you know. But in general, each monochromatic component is polarized always, okay? And so it's customary, especially in astrophysics, it's very common to describe polarization in terms of the Stokes components, the Stokes parameters. So you must have seen this before. We have a set of 4 Stokes parameters which replace the description of the electromagnetic wave. Instead of using the spectra for each of the Cartesian components, we use IQ and U and V, okay? So these are defined this way, you know. So it's kind of different linear combinations of these of E1 and E2, okay? And they are extremely important. So the first thing to note is that the Stokes I is proportional to the amplitude of the electric field. So this is the total amplitude of the electric field. Okay, so we have that, you know, you must remember that we have E1 times E1 plus E2, E2, and this is all traveling wave, a monochromatic component, okay? And so this means that the norm of E2 squared is epsilon 1 squared plus epsilon 2 squared. And so where I'm using the Eulerian notation, so this is epsilon 1 E delta 1, and this one would be epsilon 2 E I delta 2. So we just saw that basically this is proportional to the norm of the Poynting vector. Okay, so this is proportional to the norm of the Poynting vector modulo the speed of light, of course. Okay, so here, strictly speaking, we have constants to relate I, Q, and U and V with the right units. Okay, we want I to describe the specific intensity. So that's, you can see where it's going for I. Now, what about Q and U and V? So Q, first of all, Q is interesting because Q is not the sum, it's the difference. So why would we be interested in the difference? So Q is the difference between the norm, the norm of the electric field along each of the Cartesian components. So this actually measures the degree of linear polarization. Why is that?
Because if it's 0, we immediately know that's linear polarization.
So you say, Andres,
Yes.
that if Q is 0, then
we maybe should know that's linearly polarized. I'm not sure if it's, I'm just guessing.
Yeah, but it's in that direction, but that's the idea, is that well, if Q is 0, there is no polarization. It's the other way around. It is a perfectly unpolarized wave. So how do we the way to think of this is to imagine polarizers. I mean, imagine that you have two Polaroids. So we have a light that reach some piece of equipment, you know, and let's call it P1. And P1 selects E1 so that E dot E2 is 0. We kill the other linearly polarized components. Okay, and so the light, so this is I, let's call it I0. Okay, and what's coming out of here is got I1. Okay, and in this case, I1 is going to be equals to epsilon1 squared. Okay, yeah. Now imagine that we place another polarizer. So imagine that we use another piece of equipment, which would be orthogonal to the first one. This is I naught. And this is P2. And it kills the other component, letting go through only E2. And so what's coming out is E2 equals epsilon2 squared. Okay. So if we have a perfectly unpolarized wave, imagine that we have no preferential direction, that any amplitude towards E1 is the same as the amplitude towards E2. Then I2 and I1 should be the same. If it's perfectly unpolarized, it doesn't matter where I'm killing that component or that component. The radiance or Stokes I that goes through should be the same, right? If it's unpolarized. Okay, so if it's unpolarized, these two are the same. And that's the idea. If these two are the same, then epsilon1 squared is equal to epsilon2 squared. So Q is selecting linear polarization. Okay. So what about U? U is very similar, actually. U seems to be a bit more complicated, but actually U is, in order to see how U works, we define E1 prime as 1 over square root 2 times E1 plus E2. And E2 prime as 1 over square root 2 times E1 minus E2. So it's very similar to E plus and E minus, but I'm not injecting a phase difference here. This is just real. Everything is real, okay? So I want to know now, Nitya or anyone, do you have class now?
No, Professor, today I don't have class.
Okay, so we can continue a little bit.
Yes, sure, we can.
Okay. So so we plug in these two expressions into the plane monochromatic wave. So it's E is E1 like this, okay, times the oscillating exponential. So you just have to solve just the same way we just did. Okay, we did this for the E plus and E minus. Okay, but now it's the same but without the I. And so the result is very similar. Let's just copy it. Let me see. It's here. So it's going to be E1 minus E2 and E1. I think this is it. Yes. So E1 minus E2. That's the same as E1 prime times 1 over square root 2 times E1 minus E2. And E2 prime is 1 over square root 2 times E1 plus E2. And all this times the oscillating exponential, of course. Okay, so this is the electric field in terms of this new basis, prime, okay? And the amplitude, let me see if I'm doing things right. So the amplitude of along E1 prime, so this would be E1 prime. Let me write it down. E1 prime is 1 over square root 2 times E1 minus E2. And its modulus then is modulus squared epsilon 1 prime squared is E1 prime times E1 prime conjugate, and that's going to be then 1/2 times E1 times E1 conjugate. Let me see. Plus, so not minus actually, minus E1 times E2 conjugate minus E2 times E1 conjugate plus E2 times E2 conjugate. Maybe I'm going too fast. I mean, I think. What I mean to say is this: it's 1/2 times E1 minus E2 times E1 conjugate minus E2 conjugate. Yes. Yes, that's correct. Okay. And likewise, I mean, please correct me if I'm wrong or if you see anything obviously wrong. Okay. And likewise for epsilon 2 squared, we have 1 over 2 times, it's going to be the same with the signs changed for I think yeah, plus E2 times E2 squared, E2 conjugate. Okay, so this is this seems a bit of a distraction at the time at the moment. But if I take the difference between the two, epsilon 1 squared minus epsilon 2 squared, then you can see that these terms, E1 conjugate, E2 conjugate, all these amplitudes of E1 and E2 are going to cancel out. Okay, and I'm left with E1 times E2 conjugate minus E2 times E1 conjugate, which is exactly the expression for U. Okay, so we see that U is actually measuring the amplitude of the electric field along linearly polarized components in this new basis, in the E prime basis. Okay, so E prime was defined like this. E1 prime and E2 prime were defined by this linear combination, which represents it's a very simple rotation where we had E1 and E2, and E1 prime is this one, and this is E2 prime. So it's just the same story. If we set new polarizers, so we have like the same story, we use polarized light or some radiation hitting a P1 polarizer that selects only E1, so that basically we say that the electric field dot E2 prime is 0, okay? So whatever is coming out is going to be polarized along E1 prime only, okay? And it's going to have an E1 prime radiance. And so that's going to be proportional to epsilon 1 prime squared. So this is I naught. And if we have same radiation hitting another polarizer P2 prime, which selects only the E2, you know, so then so this one is 0. What's coming out is only polarized according to E2, okay? And if the incident is, if the incoming wave would be perfectly unpolarized, then the result of using a polarizer along one direction or along the orthogonal direction should be the same, okay? Hence, the difference between I1 and I2 primed should be 0. What's coming out of the polarizer should be 0, okay? In fact, the difference between the two should be 0, so that there is no preference between one direction of polarization or another. Okay, we've just seen that this difference here, E1 prime squared minus E2 prime squared, so this quantity, E1 prime squared minus epsilon 1 prime squared minus epsilon 2 prime squared is just the definition of Stokes U given here, okay? So we've seen that Stokes Q should be 0 for perfectly unpolarized waves that you should be 0 for a perfectly unpolarized signal. And Q measures then the difference in polarization, in emergent polarization, if we were to select each Cartesian component with a polarizer. U is the same, except that we've changed a bit. We've changed the basis. We've made a 90-degree rotation for the polarization basis. Okay, but it's still the same as Q. Q and U are kind of the same. Q and U are just the same linear polarization seen rotated by 90 degrees, and it's just a matter of defining what is E1 and E2. So if you choose one set of coordinates, you know, then what I mean to say is Q and U are dependent on your system of reference, okay? But together, they both represent the degree of linear polarization. They're just offset by 90 degrees from one another. And then there's this last one, V. So V is actually measuring the linear component, the circular polarization. How is that? Because, well, we've just done the calculation, so that's lucky. We've just been through the maths, we can go back, scroll up. I think we did that. E plus and E minus. Here we go. There you are. So E plus. This is it. So these are E plus and E minus. So let me write them down. E plus and E minus, E1. So I can remember this, I think. E plus has got the minus sign. Okay. Yes. E plus has got the minus sign. Let me go here, put another page. So this is what we have. So we showed this. E plus is 1 over square root 2 times E1 minus I E2. And E minus is 1 over square root 2 times E1 plus I E2. Okay. And so the idea is to write this down like that. So we have this plane electromagnetic wave, you know, like this. This is the electric field of the wave hitting a polarizer. And we can also write it down in terms of E plus. And where E plus and E minus, I remind you, are given by this compact notation. So, but with an I here. So it's very similar to the 90-degree rotation, but with an I, an additional I here. Okay. So now, what happens when I so, well, first of all, let's try and measure epsilon plus. I mean, so epsilon plus squared is going to be, so this would be the modulus of E plus squared, and that's going to be E plus times E plus conjugate. And so you can guess that it's going to be very similar to what we just worked out. So it's going to be E1 times E2 conjugate I'm gonna make a mistake. So let me go slowly. Let me write it down again. So it's gonna be 1 over 2 times E1 minus I E2 times E1 conjugate plus I E2 conjugate. And so epsilon plus squared is a half times epsilon 1 squared plus I E1 E2 squared minus I E2 E1 conjugate plus epsilon 2 squared. Good. And epsilon minus squared is going to be very similar. Epsilon 2 is with a plus. So plus is everywhere. So we have 1/2 times epsilon 1 squared plus I E1 E2 conjugate plus I E2 E1 conjugate. Oh, no, this is wrong. It's got a minus here. And the last one is minus epsilon 2 squared. Is that correct? I think that's right. No, it's not right. It's plus here. I should write it down because otherwise, you know, when I try to go too fast, I make mistakes. So this is it. So E1 conjugate minus I E2 conjugate. Now let me check quickly. E1 dash this one. Then this one is minus 1 E2. Yes. This one there is yes. And that one last one is yes, I think it's okay now. So we see that epsilon plus squared minus epsilon minus squared is then so the square model square is going to go away. So I'm taking this one minus this other one. This in green, so that's gone away with this one. This one goes away with that one, and I'm left with So it's I factor E1 times E2 squared conjugate. And the other one is minus E2 times E1 conjugate. Let's see. Well, yes, this is exactly Stokes V. So this is the definition of Stokes V. So how does that work then? So it's the same story. We have light hitting a polarizer, and this time it's going to be a circular polarizer. This one is selecting left circular polarization. So in the positive, left circular means in the positive direction of rotation. So that we set to 0, this polarizer kills the component of polarization in the right-handed polarization. And so what's coming out here is purely is I plus, so this is I naught, okay, and I plus then is proportional to epsilon plus, and that's modulus epsilon plus square, okay. Okay, so we have this polarizer that selects right-handed polarization. What about left-handed polarization? So we use another polarization, polarizer, which kills the other components. So this other polarizer is killing E plus, and it's only leaving, all that emerges from this polarizer is the minus component. So that's going to be proportional to epsilon minus squared, okay? So if light was perfectly unpolarized, if the incident radiation I naught was completely unpolarized, then the difference between the radiation emerging from the right-handed polarizer or the left-handed polarizer should be the same. I mean, there should be no difference coming out between the right-handed polarizer or the left-handed polarizer. There would be a difference only if the incident radiation had some preference, if it was somehow polarized in a given way, you know. And so this motivates the idea of using V to measure the degree of circular polarization. You know, we use V, the difference between what's coming out of each polarizer, to measure the degree of circular polarization. So now we are talking about monochromatic waves, perfectly monochromatic components. Okay, so a monochromatic component, you can see from the formula given here that the total radiance is related to the sum of V, Q, and U. So that is what you can already hint at, is that for a monochromatic wave, which is strictly elliptical or linear or circular, all these Q, U, and V are related. You know, I mean, because a given I naught can have a degree of linear polarization, can be somewhat circularly polarized. It depends on its elliptical polarization state. And so each Stokes parameter is not linearly independent. They're related to each other, you know. So it's okay. So it's fine to think of I, Q, and U and V as measurements of the degree of polarization. So Q would estimate the degree of polarization in some reference frame. So we have a coordinate system, you know, E1 and E2, and this is going to give us degree of linear polarization along one of the two components. U is the same, but for that frame rotated in 90 degrees. And V is measuring the degree of circular polarization, either right or left, in the same coordinate system as E1 and E2. Okay, and they're all related for a monochromatic wave, a perfectly monochromatic wave, okay? So for now, the usefulness of the Stokes parameter is not entirely evident. It's not completely obvious. I think it will become more obvious when we deal with quasi-monochromatic waves. Because the first thing to note, though, is that there is something interesting here. Note that I, Q, and U and V have both the same dimensions. So we can do radiation transfer on each of them. So that's handy, because if we describe the polarization state with chi, for instance, this angle here has got very different dimensions than each of the components of E. So describing the linear polarization with the phases and the amplitudes is really a pain, whereas here IQ and U and V have got the same dimensions. Now it remains to be seen whether a description in terms of IQ and U and V is complete to describe the radiation. Let's assume it is for now. Now, I would like to finish today just mentioning this fact that we'll catch up with next week. And it's the following, is that, you know, when we want to calculate the spectrum, okay, so when we calculate the spectrum, we do the Fourier transform. So let me go back a little bit here with the spectral decomposition first. So we had this. When we do the spectral decomposition, we have a signal at some point X and some electric field which depends on time. And this signal can be whatever. Strictly speaking, it moves in all over the place. Now here, I'm taking the spectral decomposition, and this is going to give me the spectrum. Now, in order to calculate the spectrum, I need to do the opposite transform. So look at equation 30, okay? I'm expressing the signal in terms of an integral of all frequencies of this of the oscillating phase, you know. Now let's go back to the opposite work. No, we want to calculate the spectrum given the signal, okay? And that's the Fourier pair, you know. I'm just calculating each spectral component in terms of the signal. But we have a problem here. Look at this integral. This integral goes over minus infinity to plus infinity. So, you know, the only way I have to calculate the spectrum of a signal is to observe it for the eternity of all times, since the Big Bang and to forever, you know. That's the only way I can calculate the spectrum of radiation. Of course, that doesn't happen in practice, okay? So that doesn't work. And so we replace these, so that we deal with this problem by saying that the spectrum actually is an average, or this is not an interval of all times, and it's and we have a spectrum that depends on time. What I mean to say is that we can indeed calculate the spectrum, but this integral is only integrated over a finite delta t. It relates to this idea of calculating you know, when you receive this the signal in a radio interferometer array, you correlate signal in two antennas, and long story short, you need to average these quantities. So we have the electric field at R1 times the electric field at some other position where you have another antenna, and you take time average, okay? And this is just the time average, you know, of a signal that depends on time. And this time average is going to be 1 over t plus delta t. Sorry, plus t. So if you want, this time average here depends itself on time, because this integration time depends on the origin t. You know, so maybe t is of order 3 seconds, you know, but then of course, like this thing, where you start doing the integration depends on time. So the resulting spectrum is going to depend on time. So that's the way you would do it with an interferometer, but it happens for any detector. You know, when you collect just the pointing vector. So just that would be the average of E cross H, and that's proportional to the average of E times E conjugate, you know, and that depends on time too. So it's just that the difference here is that I'm placing myself in the same position. That would be E at R1 times T times E at R2 times T conjugate. Sorry, same R1. So this would be for a single dish, a single antenna, or a pixel in your CCD detector array. You know, you're just measuring the pointing vector. For an interferometer, the difference is that this product, oh, I forgot the complex conjugate here, is the same as for a single dish, except that I'm cross-correcting the signal at two different positions. Long story short, this time average, either for the single dish, for the interferometer, depends on time. And so instead of writing the spectrum as constants, as complex amplitudes, as constant amplitudes like this, we inject a time dependence here. And you can imagine that this is real astronomy. This is real astrophysics. That's a real situation. The previous one was just academic idealization. Okay. And so now we need to connect this with the Stokes number and how they impact the relationship between them. But we'll do so next week. So I think that Nitya and Pratyush are traveling tomorrow. I wish you the best of luck and that you have a safe journey, that you arrive very well here in Santiago, and that you're in good shape to catch up with the lecture next Tuesday.
Yes, thank you. Thank you, Professor.
Next Tuesday, then I'll continue presenting my summary, but I'd like one of you to please help me out with presenting the corresponding chapter in Rybicki and Lightman. Given that Pratyush and Nitya are probably going to be overwhelmed by jet lag and other terrible things, I assume that Felipe, please help me out, and Andres also. Bear in mind that I expect your help with chapter 2. Okay. Ciao.
Okay, bye. Good luck.
Thanks.